Hello and welcome. We are going to have a quick lesson on curve sketching. What is curve sketching? Curve sketching is using all of the techniques from pre-calculus and calculus to, by hand, produce accurate quality graphs of functions. And this is kind of a follow-up to a skill that you learned even back in pre-calculus. And in pre-calculus we discuss all kinds of properties of functions, figuring out when they're positive and when they're negative, finding roots, end behavior, is the function odd or even, what is the domain, what is the range. These all kinds of techniques are still relevant, but now with calculus we can do things that we could not have done with pre-calculus, and that is finding where the function's increasing and decreasing, finding relative extrema, and now even determining when a function's concave up and concave down. Okay, so we did something like this at the very end of the previous class. Let's take a pretty easy function, this one here. This is a quartic, so this is a polynomial, and we can see immediately that this polynomial has roots at 0 and roots at 4. So we already sort of roughly know, even from pre-calculus, what the shape of this graph is, but now we can get a more accurate answer. So alright, let's do it. This first thing we need to do is we need to collect all the data, so to speak, so we have to differentiate this function. So let's go. I'm going to take the derivative very nice and carefully. What is the derivative of this? And we use the product rule, so it's the derivative of the first times the second. So that's 1 times the second plus the first x times the derivative of the second, and the derivative of x minus 4 cubed is 3x minus 4 squared, back inside for the derivative of x minus 4, which is 1. Okay, and now I want to factor this, so I will take out an x minus 4 squared. They both have an x, both of these terms have an x minus 4 squared in there, and when I do so, I'm left with x minus 4 plus 3x. Okay, so this factors quite nicely. I end up with x minus 4 squared times 4x minus 4, and therefore this is 4x minus 1 x minus 4 squared. That is the formula for the derivative. Okay, let's continue and let's take the derivative again, so we get the second derivative. Once again, I will use the product rule. First I'll sort of take out a 4, and now it's the derivative of the first, which is 1 times the second, plus the first, x minus 1 times the derivative of the second, and the derivative of x minus 4 squared is 2x minus 4, to the 1, back inside for the derivative of x minus 4, which is just 1. Okay, so this is pretty easy as far as things go. What now? I see that both of these terms have an x minus 4 in there, so I will take out that x minus 4, and that leaves me with x minus 4, and now I have plus 2x minus 2. Alright, so this is 4x minus 4, and that's 3x minus 6, and therefore the final version here is 4, I could take a 3 out of that 3x minus 6, leaving me with 12, x minus 2, x minus 4. So, this problem has been sort of chosen to be, easy, and one of the things that makes it easy is that it's a polynomial, so it's sort of familiar. Nothing kind of weird or crazy happens, and in fact, the function came to us in this very nice factored form, so it was easy to see what the roots were. But the derivative also is in a very nice factored form, or can be put in a really nice factored form. And same with the second derivative. Okay, so the next step is to produce sign charts for all of these expressions so we can do some analysis. Alright, well it's not always possible to make a nice sign chart for the function itself, but in this case it is. And we see from our pre-calculus background knowledge that we have a linear term, we have a cubic term, this is going to be a quartic. This quartic is going to have end behavior like this, therefore there will be a sign change at 0, and there will be a sign change at 4, since we have sort of an odd number of these. If x is a little bit bigger than 4, this term will contribute positively, but if x is a little bit less than 4, this term will contribute negatively. Therefore, the sign chart here is plus, minus, plus. This is certainly a prerequisite skill to be able to make these sign charts quickly. Okay, now let's perform a similar analysis on f prime. What do we see about f prime? Well, this is now a cubic function with a root at 1 and a root at 4, but since this x minus 4 expression is being squared, there will be no sign change at 4, because regardless of whether x is more than 4 or less than 4, this factor will be positive. So therefore, there's only a sign change at 1. So how exactly you want to do this is up to you, but most people put 4 in here anyway, but when it comes to making the sign chart, you just have to recognize that there's no sign change there. So it's a cubic, and it goes negative, positive, positive, no sign change at 4. Alright, well based on what we learned a week and a half ago, if the derivative is negative, it means that my function is decreasing, and if my derivative is positive, it means that my function is increasing. So I now know on what intervals this function is increasing and decreasing. And based on the first derivative test, since the derivative changes sign from negative to positive at x equals 1, it means that there is going to be a relative min here. But here there is no sign change in the derivative, so this is neither a relative min nor a relative max. Okay, continuing, what about f double prime? F double prime changes sign at 2 and 4. So here's 2. And here's 4, and this is just a quartic, so leading coefficient positive, the derivative, or the sign chart will therefore be positive, negative, positive. Alright, what's the significance of this? This is what we did the last class. If the second derivative is positive, it means that my function is concave up. If my second derivative is negative, it means my function is concave down, and over here my function will be concave up. Okay, and now this kind of, I think, brilliant little innovation that I got from this old teacher is to make one more row here where we combine the information in the sort of previous 2 number lines. And any number which was of interest on either the f prime number line or the f double prime number line, we add down here. So I'm going to put a 1, a 2, and a 4. And now I'm going to sort of predict or something like that the shape of this graph on all these intervals by combining this information. And here we see that my function is decreasing but also concave up. So now we can just draw a generic decreasing concave up function. Concave up functions look like this with the tangent lines lying below the curve, and a decreasing concave up function will therefore look like that. What about in between 1 and 2? Well, looking above, I see that my function's increasing and also still concave up. So now I know that in between 1 and 2, my function will be increasing concave up, and a generic increasing concave up function looks like that. Here, my function is increasing concave down. So what does a concave down function look like? A concave down function has tangent lines that lie above the curve. And so we're talking about this, increasing concave down, and over here we have increasing concave up. So we're talking about something that looks like this. Right, at this point you sort of can't go wrong because you know what this function will look like on every single one of the relevant intervals, and so now we can just do it. And there's a couple more quick things to know. Of course, f of 0 is 0, and f of 4 is also 0. Those are the roots. What is f of 1? If I plug 1 into this function, I can do this in my head. I get 1 times negative 3 cubed, so that's negative 27. And if I plug in 2 here, I get negative 2 cubed, which is negative 8, and another 2 is negative 16. Alright, finally, the goal all along is to make a graph. And so that's what we're going to do right now. And what do we see? We see that the graph's going to look something like this. 1, 2, 3, 4. Sure, let me just make sure I'm still in frame. Yeah, just barely. Okay. What do I know about this function? I know that there is a 0 at 0. I know that there is a 0 at 4. I also know that f of 1 is negative 27. Okay, so down here is 1 comma negative 27. And what's happening there? Well, f prime of 1 is 0, clearly, which means that the derivative is 0 there, so there's a horizontal tangent. And in fact, as we discussed, there is a relative min. And all of this was old, but the new thing is that at x equals 2 is also important. What happens at x equals 2? Well, the concavity changes from concave up to concave down. So this other point, this is 1, this is 2, if we just kind of ballpark this and say it's negative 16, then I have this point 2 comma negative 16, and what makes this point important is it's a point of inflection. Okay, so putting this all together, what does this function look like? Well, it's going to be decreasing concave up until 1, and so what we get is some function that's kind of, coming down here sort of sharply, but concave up on this entire interval, and then at 1 there is a relative minimum, and then the function is increasing concave up, and so we're increasing concave up until we get to 2, and what happens at 2 is something that's quite subtle, which is that the concavity changes from concave up to concave down. At x equals 4, what's happening? Well, it's also a point of inflection. The concavity changes from being concave down to concave up. The derivative is 0 at 4, which can be seen by plugging 4 into this formula, which means that there is a horizontal tangent line, but it's not a relative min or max. It's one of these situations that looks kind of like this, and we get a little bit of this. Okay, we sort of already knew from pre-calc C that this was going to look this way. The calculus is merely confirming what I sort of already felt, which is that this function is locally cubic near x equals 4. Let me make sure all that fits in there. Yeah, perfectly. Alright, so what is there to say? The only thing to say is that on this interval, the function is concave up, which means that the tangent lines lie below the curve. Here we are still concave up, so the tangent lines still lie below the curve, but then starting at x equals 2, this is what we call a point of inflection. The concavity changes, and now the curve is concave down, which means the tangent lines lie above the curve. And then there is one more change of concavity here at x equals 4, and it goes from being concave down to concave up. Alright, so what's the moral of the story? Using the power of calculus, as long as we know how to differentiate a function, and as long as we know how to make sign charts for the derivative and the first derivative, we can find all relative extrema, all points of inflections, and we can know the concavity, and therefore we can know the general shape of the graph. Okay, I'll be back in 1 minute for another problem. This one is as easy as it gets because it's a polynomial, so for the next ones they're harder problems, but I'll do less talking and explaining, and we'll just go for it. We're back. Another function, x e to the x. Let's make a graph. Alright, jumping right in, I will take the derivative and I'll do that using the product rule. So derivative of the first times the second plus the first times the derivative of e to the x, which is e to the x. Alright, so that was pretty easy, and in fact f prime is just e to the x times, if you factor out e to the x you get x plus 1. Okay, that's the first derivative. What's the second derivative? Well, we can just, again, use the product rule. It's the derivative of the first, which is e to the x, times the second, plus the first, e to the x, times the derivative of the second, and the derivative of x plus 1 is just 1. Alright, so what do we have here? We have x e to the x plus another e to the x plus another e to the x. So, okay, most people can just probably do this in their head, but if you somehow can't, you're going to have an e to the x and another e to the x, so that's 2 e to the x. And so, in fact, this is e to the x times x plus 2. Okay, this time it was pretty easy to take the derivative, and also, once again, the derivative factored quite nicely. Of course, a bunch of background knowledge going on here, such as e to the anything is positive, so we have a product of two, well, so, okay, so I can tell you exactly when my function will be positive at a glance, positive or negative, and I can do the same for the first derivative and the second derivative. So let's squeeze in the number line analysis right here. What can I say about this function? Again, since I can, I will also make a sign chart for f. And what is the sign chart for f? Well, the sign of the function is going to be determined by the sign of the x factor, since the e to the x factor is always positive. Therefore, my function will be negative and then positive. There will be a root at 0. That will be the only root. All right, what about f prime? Well, again, e to the x is always positive, so the sign of f prime is going to be determined by the sign of x plus 1. So that changes sign at -1, so that's kind of all there is there. Again, it's going to go from negative to positive at x equals 1, which means that my function is decreasing and then my function is increasing. And so once again, we will have a relative min here at x equals -1. Okay, second derivative, changing sign at x plus 2, so, or changing sign at -2 rather, determined by the sign of, okay. So what do we get? Again, negative, positive. So again, that tells me that my function is concave down and then is concave up, and there will be a point of inflection at -2. And now I make the shape chart, which combines the information in the previous two number lines. And so I care about -2, I care about -1. What's happening on the interval from negative infinity to -2? We are decreasing concave down. And a generic decreasing concave down function looks like this. And in between -2 and -1, my function is decreasing and concave up. Well, a generic decreasing concave up function looks like that. And on the interval from -1 to infinity, my function is increasing concave up. Okay, so we did sort of all the calculus first. There it is. And I was going to say something. Oh yeah, this function's weird. Okay, so you might, the previous one was a polynomial. We sort of graphed those already in pre-calc, but our graphs just weren't that accurate. Our graphs did not contain the locations of the relative extrema and the points of inflection. This function is just too crazy. You know, you would have no hope of graphing this function by hand if you were a pre-calculus student, because there's just too many sorts of weird questions. So this is truly the kind of function that you would only graph by hand as a calculus student, and it's this information which is going to sort of teach us what the graph looks like, but sort of all bets are off in terms of guessing what the shape is going to be. Unless you have some experience with this, it's not obvious at all. And what that means is that though I did this kind of calculus first, let's not neglect our pre-calculus. So we should be keeping in mind all the other sorts of things that we did when we tried to analyze functions in pre-calc. This is kind of the culmination of all of that. So, you know, even, okay, I don't want to go into all of these, but, you know, you should even for half a second ask yourself, you know, what's the domain of this function? And the answer is, yeah, I can take e to the anything, and so the domain is all real numbers. Are there any other, you know, crazy sort of things to kind of worry about or whatever? Here, I think one of the things worth exploring is the M behavior. So this is the kind of thing that we did in pre-calc, but it's the kind of thing we did, you know, even more in calculus. What happens if you try to take the limit as x approaches infinity of x e to the x? Well, it's pretty clearly obvious that both of these are growing, and so the product is just also going to keep growing. But if you want to be a little bit more you know, clear about what's going on, when computing this limit of a product of two functions, you could try to split it up as the product of two limits. And so let's just do that, just to kind of prove a point, that well, exactly what I said, splitting up into the product of two limits. And, okay, what do you know? This is obviously infinity, and this is 2, and so this is one of the things that we discussed a long time ago. If this is becoming huge and this is also becoming huge, then the product is becoming huge as well, and so this limit is infinity, of course. Alright, but when I go to take the limit as x approaches negative infinity of x e to the x, it's kind of less, obvious, maybe, what's going on here. And in fact, if you try to slow yourself down and do a careful analysis, you turns into something like this. Limit as x approaches negative infinity of x times the limit as x approaches negative infinity of e to the x. And here now suddenly, based on this amount of information, it's a little bit confusing because of course as x goes to negative infinity, this x is becoming a huge negative. But what happens as x approaches negative infinity to e to the x? Well, that's just a decaying exponential function. This is going to become very, very close to 0, right? If you plug in, 100 in there, negative 100 rather, e to the negative 100 is a tiny positive number. All right, so if you were only doing this kind of very superficial analysis, you might be very confused as to what the answer is here, because we are multiplying a huge negative number times a tiny positive number, and there is just no general rule for what to expect when you multiply a huge thing times a tiny thing. It could turn out to be huge, it could turn out to be tiny, it could turn out to be something in between. It could be 1, it could be 3, anything could happen. So some kind of more advanced analysis is going to be needed to get to the bottom of this. And okay, there is an entire sort of technique for analyzing limits that are like this, and this technique you're going to learn, later. So you don't know it yet, and therefore we're not going to do this properly. We're going to do it by just messing around. And in this case, it's really not even close. If you just try to go for try some numbers. So consider when x is like negative 1,000. That's a pretty huge negative number. Well, when x is negative 1,000, what kind of thing is this function? It's going to be negative 1,000 times e to the negative 1,000. But when I consider this expression, it's pretty clear that this is like negative 1,000 over e to the 1,000. Okay, so sure, negative 1,000 is pretty big, but e to the 1,000 is just monstrously big. And so, in fact, this is going to be like a tiny negative. So whereas I haven't demonstrated this, sort of carefully with a proof or anything, pretty much decided that this limit is 0, and that's the right answer. I'm not trying to trick you or anything. Okay, but that was a little bit hard. All right, so anything else to do? I do want to see what these numbers are, negative 1 and negative 2, before I start graphing. So what is f of negative 1? F of negative 1 is going to be negative 1 times e to the negative 1. So negative 1 e to the negative 1. So that's just going to be negative 1 over e. E is about 2.7, so we could call that like negative 1/3. And what's f of negative 2? Well, that's going to be negative 2 e to the negative 2. In other words, negative 2, okay, I happen to know, well, negative 2 over e squared, I happen to know that e squared is pretty much 7. So since e squared is pretty much 7, this is pretty much negative 2/7. And, okay, let me make sure I'm still in frame. I am, just barely. But, okay, which one of these numbers is bigger? Negative 1/3 is like negative 7 over 21, and negative 2/7 is like negative 6 over 21. So that explains that. Also, I know that my relative min is going to be at negative 1. All right, so what have we done here? We have done some side calculations to determine what the end behavior is. We have the end behavior in both directions. I have some y values now. Of course, the fact that this limit is 0 means that we have a horizontal asymptote of y equals 0. Okay, putting this all together now, let's graph the function. What does it look like? Okay, being kind of careful or whatever. Let's see, we do something kind of like that, maybe. Oh, there was one more thing I just remembered I was going to mention, which is, actually, that seems good. Yeah, that's good. Okay, so what do I care about? I care about -1 and I care about -2. And when I plug in -1, I get -7/21, but that's really like -1/e. And when I plug in f of -2, I get -2/e². And so this one is here, and this one is here. Okay, what else? This function has a root. Its only root is here at x equals 0. And furthermore, my function is negative until 0, positive thereafter. So there's a sign change at 0. And there is a left end behavior 0. So I might as well kind of draw in a sort of a dotted green line just to indicate that I have a horizontal asymptote, only sort of in that direction. What else do I know? I know that f prime of -1 is 0, which means I have a relative min. And this point, like I said, is the point -1 comma -1/e. And then I have this other point, this -2 comma -2/e² point. What's that? It's a point of inflection. It's the place where the concavity changes from concave down to concave up. So though this function is quite exotic, if you sort of just lock in and do all these derivatives correctly and make all these sign charts correctly, it's perfectly possible to graph this function. What's it going to look like? It's going to be decreasing concave down from time -∞ to -2. And so you have to just draw our function, decreasing concave down. What happens at -2? Point of inflection, and the concavity changes from concave down to concave up. So there's this kind of subtle change here. And now, staying concave up, there is a relative min at -1, and subsequently, my function is just increasing concave up. And so we're going to increase concave up. We're going to have our last sort of root over here, and then this function is just going to go straight up in the air. In fact, probably increasing, way more steeper than that even, actually. Okay, but what are the key features? The key features are, there's this relative min here, and then we can see from our graph, I've exaggerated a little bit, but that the tangent lines lie above the curve over here because it's concave down. But then what happens at -2 is there is this point of inflection, and subsequently for the rest of the function, the tangent lines lie below the curve. And so the new thing that we learned is that there is a point of inflection here at x equals -2, and this, of course, is a relative min. Okay, I think that pretty much covers it. All right, be back for one more function. All right, we're back for the third graph. F of x equals e to the 1/x. I know you've been waiting your entire life to finally know what this particular function looks like, and also you want to be able to do it by yourself, by hand, that is, without using technology. Okay, let's go. A lot of things to talk about here, pre-calculus wise. So first of all, e to the anything is positive. And so since e to the, I'll just say anything, is positive, we conclude that this function is always positive. So f of x is always positive. In other words, this function has no roots. All right, so that's a kind of an important pre-calculus thing to get out of the way right away. Also, what is the domain of this function? Well, pretty much screaming at me this formula that I cannot plug in 0. So anything else is fine though, so the domain is going to be everything except 0. Furthermore, there is going to be some crazy stuff happening at 0, because if you plug in a very tiny number, then 1 over a tiny number is going to be huge, and so we might expect some sort of dramatic kind of discontinuity happening at 0. So we better check that out. So let's just do this part first. That is, calculate the end behavior is something that we need to do. And also we need to see what's going on near 0. Okay, so let's just do 4 limits. Let's take the limit as x approaches infinity of e to the 1/x. the limit as x approaches negative infinity of e to the 1 over x, the limit as x approaches 0 plus of e to the 1 over x, and the limit as x approaches 0 minus of e to the 1 over x. Sort of like all of these I want to know. Alright, let's just kind of talk them out. If you plug in a huge number like 1,000,000 here, you get, 1 over 1,000,000, that's going to be a tiny positive. And what is e to the 0 plus, so to speak? Well, e to the 0 is 1, and if you plug in a number that's a tiny bit more than 0, then what you're going to get is something that's a tiny bit more than 1. So the answer to this limit is 1, but for purposes of graphing, it's nice to know that it's going to be, in fact, a little bit more than 1. Okay, what about over here? Well, now, when you plug in like negative 1,000,000, you're going to get 1 over negative 1,000,000, so that's going to be a tiny negative. So this is going to be e to the 0 minus, and what is e to the 0 minus? Well, again, e to the 0 is 1, so e to the something a tiny bit less than 0 is a tiny bit less than 1. Okay, what now? Well, if you plug in a tiny positive, the reciprocal of that is going to be a huge number, and e to the huge is huge, so, that's kind of like an e to the infinity type situation. That's infinity. And finally, if you plug in 0 minus here, 1 over 0 minus is going to be like negative infinity. And what is e to the negative infinity? That is going to be a tiny positive number. Alright, so quite a lot of pre-calculus going on already. What else? I guess we just jump in with the calculus now. So let's take our function. Maybe we want to write it out sort of as, e to the x to the negative 1. For purposes of applying the power rule, maybe it's, it's kind of ugly to write it that way, but maybe that's a good idea or something. Alright, let's take the derivative. What happens? This might get a little bit messy. So what is the derivative of e to the something? Well, it's e to the something. So e to the, x to the negative 1. Back inside for the derivative of the something. So doing the chain rule here, what is the derivative of x to the negative 1? Answer, it's negative x to the negative 2. Yeah. So, so true. So what do we really have here? To rewrite this in a kind of a more algebraically friendly form, our real function is e to the 1 over x. Our derivative function is negative e to the 1 over x squared. Yeah. Okay, looking good. What next? I guess I need the second derivative. How to do this? I guess there are a lot of ways. We could just do the quotient rule, or we could do the product rule. I actually sort of prefer to just do the product rule in this situation, so I'm going to do that, but you can also do the quotient rule. You'll get the same thing. Okay, so doing the product rule on this form right here, what do I have? I have the derivative of the first. Oh boy. Okay, what is the derivative of e to the x to the negative 1? Well, we kind of did that already. So it's just going to be, e to the x to the negative 1 times negative x squared. So that's the derivative of the first times the second, so negative x squared, plus the first, which is e to the x to the negative 1, times the derivative of the second, and what's the derivative of negative x to the negative 2? Answer, it's 2x to the negative 3. Alright, so I guess I'm kind of gross thing here. Yeah, that's just right. Probably. I guess I'm kind of gross thing here. What do I have here? Man, I don't know. I have e to the 1 over x times, this should be negative 2, I guess, right? Yeah. Negative x to the negative, let me just double check my work. Derivative of the first is boom boom times the second. So yeah, so those are both negatives. So these negatives will cancel and I get e to the 1 over x to the negative 4 plus e to the 1 over x times 2x to the negative 3. Alright, so simplifying this, I can take out an x to the negative 4, And so I get e to the 1 over x, x to the negative 4, leaving me behind with, well, just a 1. And over here, this will be 2x. Because x to the negative 4 times 2x is 2x to the negative 3. Okay, so believe it or not, my my second derivative function will be like this. It will be it'll be e to the 1 over x, 2x plus 1 over x to the 4th. Whew. All right, so that's f double prime. All right, so what do I have here? I have all the things that I need to do this problem. I have my function. Here it is. I have my derivative. Here it is. And I have my second derivative. Here it is. And now I'm going to put these all together and make my shape chart and everything. All right, let's do it. Let's go. So, what's the function going to look like? Can I tell you when it's positive and when it's negative? Well, okay, this is just almost a little bit silly because, as we already discussed, this function is always positive. So that was maybe a waste of a line. But, all right, continuing on. What can I say about f prime? F prime, here it is. Well, e to the anything is positive and x squared is also always positive. Therefore, f prime is just always negative. And however, that's true. However, let's not forget that this function is undefined at 0. And in fact, something sort of crazy happens at 0. I mean, we didn't even discuss this. But, you know, if x is a tiny positive number, this function's off at infinity. But if x is a tiny negative number, it's down at 0. So there's certainly some sort of crazy jump happening. In fact, it's like an infinite jump that's happening at x equals 0. Therefore, it's probably a good idea to include 0 on our number line. And even though my function is decreasing because the derivative is negative, it's kind of decreasing when x is negative, and it's also decreasing when x is positive, but that doesn't mean it's a decreasing function on the entire interval of real numbers. We will see as the graph starts to kind of emerge what I am talking about. Okay, what about f double prime? It's going to have a sign. Okay, again, the denominator is always positive. This factor is always positive. This is just a linear factor which will change signs at -1/2. And so the f double prime number line, also including 0, but there's no sign change at 0. Over here at -1/2, there will be a sign change. And this will change sign from negative to positive at -1/2. And so we're talking about negative to positive. So what does this mean? It means that my function is concave down, concave up, and finally concave up. All right, putting it together, this shape chart here, including -1/2 and 0, what do I get? I get that my function is decreasing concave down. So a generic decreasing concave down function looks like this. Decreasing concave up, so like that. And over here it's still decreasing concave up. Alright, but when I go to try to put all this information together, there's one more sort of little piece of bookkeeping, which is what is f of -1/2? Well, it's e to the, it's e to the 1 over -1/2, which is just e to the -2. So that's just 1 over e squared, and that we agreed was like 1/7. Pretty much. Yeah. Okay, what does this function look like? Wow. Let's see. Yeah. How to plan this out. maybe we'll do something like this. The function's always positive, so we can just kind of plan it out like that. What do we know about this function? Do we know anything? Well, there are no roots. Here's another thing that we know. I'll put 1 right here. Yeah. And I'll put -1/2 over here. And I know that when I plug, maybe I'll make 1 even higher. Yeah, so there's 1 over here, something is like -1/2. Okay, let's start adding in some information. Point of information number 1. The right end behavior is 1 plus. Okay, so I know that the end behavior of my function looks like that. Okay, great. I know that the left end behavior is 1 minus. Alright, so it's also true that, 1 is a horizontal asymptote sort of in both directions. What next? When x is a little bit more than 0, this function's off at infinity. So I have actually a vertical asymptote at x equals 0 as well. And however, when x is a tiny negative number, this function is going to be basically 0. Alright, so I think what we have is like a hole at 0 because this function will never be 0, clearly, but as x approaches 0 minus, the function is approaching 0. And then the final thing to do is, I guess, add in this little fact that I know right here, boom, this point of inflection, this is 1 over e squared, is happening at -1/2. And now I just kind of follow the directions. What are the directions? My function is decreasing concave down. So I start at -infinity, a little bit less than 1. And my function is going to be, there are no relative extrema. It's just going to be decreasing concave down. And then, what happens at -1/2? It changes to be decreasing concave up. And then, there is, as x approaches 0 minus, my function getting really, really close to the origin. But then, as soon as we switch to tiny positive numbers, my function is in some completely different location. In fact, it's up here at infinity. And so that's the extent to which this decreasing is perhaps a little bit misleading. It's decreasing until 0, but then there's a discontinuity. If there's a discontinuity involved, be ready for that. Now my function is concave up, decreasing. And so the right end behavior is 1, and so what we're talking about is just something that looks like that. So this function has only sort of one, there's a couple of fascinating points, I suppose. This point is -1/2, 1 over e squared. Why do we care about this? It is a point of inflection. What makes it a point of inflection? My function is concave down to the left of that point, tangent lines lying above the curve, then it switches to tangent lines lying below the curve. But then there is this infinite jump discontinuity at 0, taking me way up, and then my function is concave down with the tangent lines lying below the curve for the entire way. Okay, this was kind of a mix of very normal problems and very exotic, weird, crazy problems. But basically, the moral of the story is you can graph anything by hand if you know how to take the derivative and you know how to factor those derivatives. So this was our lesson on curve sketching, and you have more problems to do on this, so goodbye.